Hi everyone and welcome to PrepFusion. So I am Anish and today we'll be starting the lecture 6 of this state space chapter. So previous lecture we learned about eigenvectors and eigenvalues and few terms. In this we'll learn about the properties of eigenvectors and eigenvalues. Okay, and then we'll summarize all of them, right? So first I will take few examples. Okay, like as I had to stop the previous lecture. So first example what I had to take is, let's say I have a matrix A, right? Okay, whose which is defined like this, which is 0 to 2 0. Okay, 0 to 2 0, and I have another matrix. Let's say this is A1. Okay, this is A1, and I have another matrix as A2. Okay, which is defined like this. Okay, 2 minus 2 and 0. So what do you understand from this matrix and this matrix? Okay, just observe these two matrices, and from your basics you can say, right? I hope you already studied a bit of matrices in 11th 12th. So what we have studied is that, like, if I make a transform, right? If I make a transform, right? So the transform, sorry, not the transform, if I take the transpose of this matrix, that will be equal to the matrix itself. What do you mean by transpose? That the columns becomes rows and the rows becomes columns. So 0 2 becomes a row and 2 0 becomes another column. So what we observe, it is same as the previous matrix only, same as the previous matrix only. So yeah, this is what basically this is like the what this matrix is. This matrix is symmetric. And what is this matrix? So what you observe here is, if you again take the transpose of this, you get 0 minus 2 and 2 0. But this isn't the same as previous one. But if you multiply a minus sign with this one, you get the same matrix. Okay, you get the same matrix. So this type of matrix is known as skew symmetric matrix, and this one is known as symmetric. Okay, so yeah, these are the definitions. I hope you already know all this, but still I explain it to you. So now, right now, what you will do is like find the eigenvalues of this matrix, right? Find the eigenvalues. So find eigenvalues of lambda 1 and of A1 and A2. A1 and A2. Okay, so what will be the the solution here is, like first let's find the eigenvalues of A1, right? So eigenvalues of A1, what we will do, again do that A minus lambda I, make the determinant as 0, right? So this will become like 0 minus lambda, which is minus lambda only. I will write this directly now, and 2 minus 0, so this is 2 only, and this is 2 minus lambda, so sorry, 2 minus 0, again this is 2 only, and this is 0 minus lambda, so this is lambda only. So this is equal to 0 only, right? So this becomes lambda square minus 4 equals to 0. So lambda equals to plus minus 2, right? Lambda equals to plus minus 2. So I have two eigenvalues, which are lambda 1 equals to 2, let's say lambda 2 equals to minus 2. Okay, so yeah, these are my two eigenvalues. Okay, now let's find the eigenvalues for the second matrix. This was the part 1. Okay, this was the part 2. So this is simply A2 minus lambda I, right? Again, which is equals to 0. I'm just varying the lambda, okay, and finding the value for which this determinant becomes 0. So again, if I solve this, right, what do I get? I get, again, this is minus lambda, this time this is 2, this is minus 2, and this is again minus lambda, equals to 0. So what is the equation that I get now? Here is lambda square plus 4 equals to 0, and hence lambda equals to plus minus 2i. Okay, lambda equals to plus minus 2i. What do I see is that this is complex. This is actually purely imaginary, but you can say like, yeah, complex falls under purely imaginary, right? Sorry, purely imaginary falls under the complex numbers. So this is complex number, right? So like our eigenvalues are complex, so no eigenvectors will exist for complex eigenvalues. Okay, no eigenvalues will exist for complex eigen okay, sorry, I wrote no eigenvectors will exist complex eigenvalues for complex eigenvalues. Okay, so yeah, this is basically that, right? So basically, why let's take example, right? So what is the example? So example that I should take is this one only. So I have this two eigenvalues, right? So what I will do, find like vector v1, right, for this equation. So what I will do, a minus lambda 1 I into v1 equals to, oh sorry, I'm doing this wrong, I should do it like this. Okay, we can solve like that also, but I'll do it like this. So a times v1 equals to lambda 1 times v1. This is a2, right? This is a2. So here I should write here a2. So a2 times v1 equals to lambda 1 times v1. Okay, so let me put lambda 1 here and a value of a here, and let me take v1 as x1 y1. So a is 0 2 minus 2 0 x1 y1, which is equals to lambda 1 times v1. Okay, lambda 1 times v1. So lambda 1 is 2i only, 2i times x1 y1. Okay, x1 y1. So what does it become? It becomes like, let's solve the first equation. So 2y y1, right? 2y1 equals to 2i x1. Okay, 2i x1. So y1 equals to I times x1. So this is the first equation basically. So I'm doing it like this only. Okay, now what is the second equation? Second equation is minus 2 times x1 equals to 2i y1. So this is the first equation, minus 2 times x1 equals to 2i y1. Okay, 2i y1. Okay, so what is x1 equals to? X1 equals to minus I y1. Okay, x1 equals to minus I y1. So let me put this value of x1 in this equation, right? In this equation. So if I put this value, right, so what do I get? y1 equals to I times minus I y1, right? So this becomes simply y1 equals to y1 only. So main thing is that we'll get complex eigenvectors, right? So yeah, eigenvectors, the real eigenvectors won't exist. So what will happen? Y1 can take any value. Okay, also x1 is related with y1 like this, x1 equals to minus I times y1. So what will be basically my equation? Let me like the eigenvector, right? So v1, it will be simply c times this is 1 only, this is like, let's say this is 1 only, now this is minus I. Okay, our eigenvector becomes like the complex, right? Complex. So this is we won't use this eigenvector. So the eigenvectors also becomes complex for complex eigenvalues, right? So in this way, right, like what does this I means? Like in physical terms, it actually rotates the value by 90 degrees, right? It makes it orthogonal, because let's say how like intuitively how you can understand. Let's say I have like, what is the I plane, right? This is 1, this is I, this is I square, and this is I cube. I hope you know this, right? How, like this I, right? This is I only. If I do I square, I come to minus I. Okay, I come to minus I. And if I do I cube, this is sorry, if I do I square, this is minus 1 only. So this is the opposite of this one. And if I do I cube, this is minus I only. Okay, this is, which is the opposite of this one. Okay, so now if I multiply anything with I, right, it rotates it by 90 degrees. So I hope you understand this. This is the real part, real component, and this is the imaginary component, right? And this is the negative of the real component, and this is the negative of the imaginary component. So this is how the axis is made. So if I multiply by I rotate by 90 degrees. So to get the vector, right, I have to rotate by 90 degrees, which is only possible in imaginary, like the complex axis, right? So for our case, what we will say is, like, for complex eigenvalues we get complex eigenvectors. Okay, that is the main important factor. Okay, because like scaling factor will be complex, that's why we have to multiply with complex eigenvector to get a real matrix, right, here, to get a real matrix like this. Okay, so yeah, that is one important thing to note here is. So yeah, that was the important point to note. Let's now, like, for symmetric, what do we know? We are getting simply real eigen values. So just this is a point to notice, that for symmetric matrices we'll always get real eigenvalues, and for skew symmetric matrices we'll always get imaginary eigenvalues, right? So these 2 points just keep in mind. I will write all these points in one note. So you take another symmetric matrix, you take another skew symmetric matrix, you find the eigenvalues, but you will see that these symmetric matrix eigenvalues will always be real. Okay, and skew symmetric would always be imaginary, purely imaginary, basically. Okay, purely imaginary. And yes, for purely imaginary values, the eigenvectors will be also complex. Okay, eigenvectors will also be complex. So these things you have to keep in mind. And for real, obviously the eigenvectors will be real. Okay, so yeah, this was it for symmetric and skew symmetric. Now one more special matrix we have is that eigenvectors for identity matrix. Okay, eigenvalue for identity matrix. So what will be the eigen value for identity matrix? So simply, right, it is A equals to, what is my identity matrix? 1 0 0 1. Okay, so what are the eigenvalues for this one? So eigenvalues, right, eigenvalues for this one will be 1 and 1 only. So this is again like symmetric matrix, right? This is a very special matrix, symmetric matrix. If you do like 1 minus lambda, this becomes 1 minus lambda, and this becomes 1 minus lambda, then 1 minus lambda whole square equals to 0. So lambda equals to, lambda 1 equals to 1 and 1 only. Okay, but the interesting fact is, how many number of eigenvectors this has? Tell me, does this have 2 eigenvectors, or does this have only 1, because they are same, right? Eigenvalues are same. Or does this have 0 eigenvectors, or how many does it have? Count and say to me. So the interesting fact over here is, it has infinite eigenvectors. How? Just take one thing for to understand, right? Just keep one thing in mind, that this is the identity matrix. So if I multiply any identity matrix with a vector, right, I will always get the vector back. That is the main property of the identity matrix. The name suggests, right, identity. If I multiply 1 with anything, I will always get that anything back, right? 1 times 2 is 2, 1 times 3 is 3. For matrix also same. 1 times anything, v will give me that only. That's the basic property of identity matrix, right? So whatever v I put here, it will always satisfy this equation. Okay, so hence identity matrix has infinite eigenvectors. Identity matrix has infinite eigenvectors, right? Identity matrix has infinite eigenvectors. So, but the thing to note here is it has only 2 eigenvalues. It is only 2 eigenvalues. Okay, so yeah, this is the main thing to note here is, so like I told you, I like explain it to you why is that it has infinite. Why? Because whatever vector we multiply, right, we get back the same vector itself. That's the property of identity matrix. So yeah, this is a very special like matrix, that every matrix is a eigenvector for identity matrix. Okay, so yeah, that was one very beautiful property of identity matrix. Okay, so yeah, I think that's it. Now we'll study the properties of eigenvalue. Okay, what are the properties of eigenvalue? But first let us understand a bit of about the characteristics equation, right? So we have to find a relation about the characteristic equation of the form of the characteristic equation and the matrix itself. So we'll try to understand here right now. So form of characteristics equation. So what is the form of characteristics equation? So basically, right, so if let's say I have a matrix, like the same matrix again, 2 1 0 3, right? So this is a 2 cross 2 matrix. What were the eigenvalues of this? So again, like if I solve for this, we can simply solve for this, right? What will the characteristics equation? So this is simply a minus lambda I, this is equals to the characteristics equation, right? So now let me solve for lambda, right? So if I solve for lambda, this is 2 minus lambda, this is 0, this is 1, this is 3 minus lambda, which is equals to 0, which is equals to 0, right? Now what equation I get is 2 minus lambda times 3 minus lambda equals to 0 itself, equals to 0 itself. So what are the values of lambda? Lambda equals to, okay, I will not solve for lambda this time. What I will do, I will write the equation. I will write the equation itself. So what is the final equation I get? If I solve, right, lambda square plus this minus 2 lambda minus 3 lambda, so we get overall minus 5 lambda plus 6, right? So this is lambda square minus 5 lambda plus 6. Okay, so this is my, what is this? This is my characteristics equation. Okay, so yeah, this is my characteristics equation. So now, right, now basically, can I find any relation with the elements of the matrix and the form of the characteristics equation? I see a 5 over here. Also I observe that if I add these two elements, right, I get 5. So what does this mean? So this is basically the sum of the leading diagonal elements. Okay, This is basically sum of the leading diagonal elements. Okay, so this is basically what this represents. Okay, and what does this number represent? Okay, lambda square and lambda, I know this will be second order equation because this is 2 cross 2 matrix. So according to the order of the matrix, my highest order polynomial I will get is 2, right? But what is the what is this value represent? Just from my mouth it came up. Okay, so repeat, what is it? It is basically the determinant of the matrix. So what is the determinant of this matrix? It is 2 times 3 minus 0, which is 6 only. So this, right, let me take this to the bottom. This represents the determinant of the matrix. Okay, this represents the determinant of the matrix. So yeah, this is basically the form how we write the characteristics equation for a 2 cross 2 matrix. So also, what do we call this? Sum of leading diagonal elements, there is a name for this, that is the trace. Okay, so the name for this is trace. Okay, so what is trace equals to? Trace equals to summation I equals to 1 to n, the number of eigenvalues lambda I. So I am summing up each of the lambda I where this is the summation of the eigenvalues. This is also another meaning for the the definition for the trace, or what I can write here is, it is a sum of the leading diagonal elements. Sum of the leading diagonal elements. Let me copy this and paste this over here. Sum of the leading diagonal elements. Okay, but the thing is, in the equation, right, just keep in mind that this will be with a negative sign and this will be with a positive sign. Okay, sum is 5 only, sum of the leading diagonal elements is 5 only, but at the coefficient a negative sign will also come. How do I used to remember it? From start, if it is a third order, what will happen? From start, the lambda cube will start from plus. I will explain in the next example for a 3 cross 3 matrix. Start will be plus, then I will go to negative, then a plus. Okay, the sign will keep on interchanging for each terms. We will understand it more in better manner in the next example for a 3 cross 3 matrix. So yeah, that is the definition of trace of A, right? Trace of, what is trace of A? This is trace of A. Okay, so this is basically the definition. Now this number, right, represents the determinant of A, which can also be written as the product of the eigenvalues. Okay, this is a characteristics equation, right? And we know what does this represent? The roots of the equation. What does this represent? The roots of this equation represents the sum of the roots are this, right, and the product of the roots are this. So from that concept, from the concept of quadratic equation, we can also understand that this is the sum of the roots, which is basically the eigenvalues themselves, and this is the product of the roots, which are the eigenvalues. Okay, so yeah, from here we get this relation, right? So yeah, now what is the determinant of A? What is the determinant of A? So basically, determinant of A is what we can say is the product of the eigenvalues. Okay, by product we represent it as pi. Don't get confused. Okay, just understand this is just a sign for products, as sigma was for summation. Okay, sigma was for summation, and this pi is for product. Simply we're using the multiplication operator, that's why pi comes up. I equals to 1 to lambda I, right? So it is a product of all the eigenvalues. Okay, yeah, that is basically what we can say. Okay, yeah, this is the relation. Okay, as trace was new term, that's why I have to explain it a bit more. Determinant you already know, it is the determinant of the matrix, and lambda is basically the product of each eigenvalues. This pi lambda is product of each eigenvalues. So yeah, this is how we can write a second order matrix of characteristics equation. Now what I'll do, I will take another example of 3 cross 3 matrix. I will not take an example, I will basically totally write the form of how we can write the characteristics equation of a 3 cross 3 matrix. So I will not derive it. Homework is for you. Take a 3 cross 3 matrix and write the characteristic equation in this form. Okay, what I told, then cross verify whether I told you correct or not. Okay, that is the homework for you. So form of characteristics equation okay for 3 crossing matrix. Okay, so what will be the form? So basically, right, so let's say I have a 3 crossing matrix A and it has eigenvalues lambda 1, lambda 2 and lambda 3 eigenvalues. So my characteristics equation, right, first thing to note is what will be the order. The order will be third, right? The order of the characteristics equation will be 3. Okay, third order polynomial basically. So it will start with lambda cube, right, and at the start it has positive sign. Now the next whatever term will come with a negative sign, so we'll write negative over here. Then what we'll do, this will be the trace of A, this will be the trace of A. So this will be simply lambda 1 plus lambda 2 plus lambda 3, okay, into lambda square. What does this represent? This represent the trace of A, right? This represents the trace of A. Okay, so and now what is the next term? Next term will come with a plus sign. Okay, next term will come with a plus sign, and this is basically, what is this? This is the product of the eigenvalues. Okay, but this time, right, not all of the eigenvalues at once, product of two eigenvalues. Okay, this will be lambda 1 times lambda 2 plus lambda 1 times lambda 3 plus lambda 2 times lambda 3. Okay, so this is product of two eigenvalues. Okay, not repeating, right? So we could have also written here like lambda, again lambda 2 here, lambda 1 here, that would have been repeated. So not repeating, right? Simply the three terms but the product of two eigenvalues. So again this is with plus. Now I will end with minus. Okay, I'm alternating the signs, right? So this, what will be this? This will be the product of the eigenvalues, which is lambda 1, lambda 2 and lambda 3, now which is equals to 0. So this is basically the product of eigenvalues, right? So yeah, that is basically what how the characteristic equation we can write for a third 3 cross 3 matrix. Okay, third order matrix. So homework, I told you take an example and you derive, like you solve the characteristic equation, and there you check whether all these coefficients, right, are correct or not. If they are not matching, then there must be some mistake in your calculation. Okay, so yeah, this was basically it for the form of the characteristic equation. Now we'll know the properties of eigenvalues, right? Properties of eigenvector and eigenvalues. So what will be the properties? Basically, right, basically the first property is, already I proved this one, that for a symmetric matrix eigenvalues will be, for a symmetric matrix eigenvalues will always be real no matter what, always be real. Now just the converse of this, for a skew symmetric matrix the eigenvalues will always be complex. Okay, or you can say imaginary. This is the second property. Let me take this here. skew symmetry matrix eigenvalue will always be imaginary. Okay. Now what is the third property? Like third property is, I will prove this one to you, that if I have a matrix, right, if I have a matrix that let's say I have a matrix of 3 cross 3, right, I have a matrix of 3 cross 3. Now it has eigenvalues of like lambda 1, lambda 2 and lambda 3, lambda 1, lambda 2 and lambda 3. Now what will be the eigenvalues lambda dash for a plus I? Okay, what will be the eigenvalues for a plus I? So like what will be the eigenvalues? Simply, right, it will be lambda 1, but let's say I am writing it like ni, okay, or ki, it will be simply lambda 1 plus k, lambda 2 plus k and lambda 3 plus k. Now you might say like how is this possible? Is this possible with any other matrix? That's simply, right, if I just multiply, multiply basically, then will I get the same eigenvalue, same same eigenvalue, just added, right, just shifted. So the answer is no. The answer is no. Why? Because let me prove it to you, then you will understand that how do I get the eigenvectors. Basically this a, right, this a times v1, I get lambda 1 times v1, right, for this particular eigenvector I get this eigenvalue. Now if I make a to a plus I ki, a to a plus ki, what do I get in this equation? A plus ki times v. Now I am just expanding this. What do I get? A times v plus ki times v, right. Now what is a times v? A times v is simply lambda 1 times v1, right, and what is simply like I times v? It is v only. So this is equals to lambda 1 times v1 plus k v1 only, right, k v1 only. So what I can take? I can take v1 as common. Okay, what I get? Lambda 1 plus k into v1, right. So yeah, this is the proof. What is my eigenvalue? Like it is like lambda 1 plus k this time. Okay, so this is the proof. Okay, let me write this in the next page, so you will understand better. Okay, you will understand better. So this is my proof basically. So yeah, now, right, so is this applicable for any other matrix? No, because this I times v, okay, I times v will happen only when like it is an identity matrix. If it is any other matrix other than a, right, other than a, then we'll be in trouble. Okay, we'll be in trouble and we won't be able to solve like this. Okay, that's why the proof is very important, like why it works for identity matrix and why it doesn't work for any other matrix. So yeah, this was my third property, right. Now let's understand the fourth property. It's same only, right. Fourth property is that trace, right, trace of a equals to simply the summation of the eigenvalues. Okay, like this is important, you should like understand the terminologies of all this. Summation of the eigenvalues and the determinant of a is simply the product of the eigenvalues. Determinant, or I can write like this is also written like this also, like trace of a equals to this. Okay, and determinant of a equals to the product of the eigenvalues basically. So this is I times 1 and lambda I times 1 and lambda. Okay, now what is the sixth form? What is the sixth form? So the sixth form, right, if one eigenvalue is 0, then like the matrix will be singular. By singular, what do you mean? the determinant is 0, okay, or the inverse also doesn't exist, okay. So if one eigenvalue is 0, then matrix will be singular, okay. Now why is this the case? If one of the eigenvalue is 0, right, then if I multiply anything with 0, so what is the determinant of A? It is multiplication of all the eigenvalues. If even one of them is 0, then this whole multiplication becomes 0. So what will happen to the determinant? It will become 0, okay. So if it is 0, then what will happen? Like it will be singular matrix, right, because the determinant because the inverse won't exist, because for inverse we have to find the determinant, and determinant comes in the denominator. So yeah, determinant won't exist, that's why this matrix is called inverse won't exist, that's why this matrix is called singular, okay. Well, whenever the determinant is 0, the matrix is called as singular, okay. And is the vice versa true? If matrix is singular, then is the lambda eigenvalue 0? Yes, but in this case there will be at least, okay. So in the 7th point, what I will write here is, like if like the A is singular, if A matrix is singular, then if a matrix is singular, then at least one eigenvalue will be 0. There can be multiple, right? So if I have like one eigenvalue 0, 0 times anything else is 0 only, but 0 times 0 also, and anything else is also 0. So at least one of the eigenvalues will be 0, but there can be more eigenvalues 0, right? So yeah, then okay, let me write this better. Will be 0. It can be more also, okay. Okay, at least one of the eigenvalues will be 0, okay. So what is the the next property is, like next important point is, now let's say I have a matrix of 5 cross 5, okay, 5 cross 5. Now it has 3 eigenvalues which are equals to 0, okay. Now can you say anything about the rank of the matrix? Okay, can you say any of the about the rank of the matrix, or about the the what do you call, about the dependency and independency of the columns of the matrix? So tell me, if 3 eigenvalues are 0, then what will be my rank of the matrix? Or you can understand from space also, like that what I told you in the first one, right, what span it covers, right? You can understand from there also. If 3 of my eigenvalues are 0, how much span it can cover? It can cover 2 2 span, right, 2D span basically, because we'll have 2 columns which are independent of each other, and all the other other 3 columns will be dependent on these 2 columns, linear combination of these 2 columns, right? So all the other 3 columns will be dependent on these 2 columns. So these 2 columns are independent, distinct eigenvectors we get, but all the other 3 columns will be dependent. Then what will be my rank? Then rank will be basically 2, right? Rank will be basically 2, okay. So here what does this signify? It signifies 3 columns are dependent on the other, linearly dependent. Okay, let me write it here. other two columns. Okay, so yeah, this is the main important factor. So as we have only two non-zero eigenvalues, so two non-zero then what we'll have, we'll have simply two vectors which are linearly independent. So let me write this in the next page. I don't have enough space here. Independent, right? So yeah, this is the main crux of this of this main point, right? So yeah, this was the 8 point. Okay, so now the coming back to the 9 property. Basically 9 property, this is a very very important property. Okay, for this we are studying this much. Okay, for this we are studying like this much of eigenvectors and eigenvalues for this property. So just listen to me very carefully. Okay, very very important property. So what is the basically the definition of eigenvectors? So if I have some matrix A and I multiply it with, transform it with eigenvector v, right, v1, I will get a scaling factor of lambda 1 and I will get the same direction as the eigenvector itself. Okay, it will not shift its direction or change its direction. Okay, it will just scale. So now this matrix is, let's say, n cross n, right? Now what does this mean? Just tell me, what does this mean? What I am doing, I'm simply like summing each of the eigenvectors, like adding each of the eigenvectors, right, and multiplying with the matrix. Okay, like I will get n eigenvectors, right? Now for now understand, I have n distinct eigenvectors. So this is important. I have n distinct eigenvectors which are basically like not distinct, n linearly independent eigenvectors. So this is v of n. Okay, now what will be my right hand side? You explain what will be my right hand side. So a, right, a times v1 is what? V1 is a column matrix, right? Column matrix. Okay, so simply a times v1, what I will get is, yes, lambda 1 times v1, right? Lambda 1 times v1. Now again, right, law of associativity. So e times v2, what do I get? Is lambda 2 times v2, right? Okay, this is the scaling factor for the second eigenvector. Now again, this a times v3, what will I will get is lambda 3 times v3, and this will keep on going on until the last eigen value. This is lambda n times vn. Okay, so yeah, so this is only valid for n linearly independent eigenvectors. So we have in linearly independent eigenvectors. Okay, so yeah, now right, now what I can do is I can compress this. These are just column vectors, right? What I will do, I will write this in one matrix itself, which are combination of all the column vectors. Okay, combination of all the column vectors. So I can compress this equation like this. This is a matrix times this v vector. Now what is this v vector? Okay, this v vector is the combination of the column matrix. I will write the whole equation and I will explain it to you. So this is equals to v1, v2, v3, and this will keep on going on until vn. Okay, and what is it is getting multiplied with, okay, this part is very important, so let me reduce the size. So yeah, this will be like this matrix, right? Okay, lambda 1, lambda 2, lambda 3. Now this will keep on going on, okay, and I will have lambda n at the end, and these, all of these are 0. This will go on till here, okay. This will be also 0 0, this will be also 0 0 0 0. After this also we're getting 0, and all these are coming down, like all of them are filled with zeros, right? This is 0 0, okay. So what is the order of this matrix? The order, right, of this matrix is n cross n, and this matrix is known as diagonal matrix. Okay, so basically, right, if I multiply this v1, okay, this is a column matrix. Just understand, this is a combination of column matrices. So like this v1 is something like this, x1 y1, like this, okay. Now this is x2 y2, and this is going on like until the whole column. This is x2 y2, okay, and this is x3 y3. So what is happening, what I am doing, I'm just multiplying this with row into column, right? So what I am doing, x1 times lambda 1, okay, then y1 times lambda 1, and z1. So this first column is always getting multiplied with this row, right? So I'm always getting the combination of this eigenvector, lambda 1 times v1, okay. So yeah, this is the main thing you have to understand, that what I am getting is this v1 is only getting multiplied with this lambda 1. That's why other are zeros, okay, other elements are zeros in this particular row, and this v2 is only getting multiplied with this lambda 2, okay. So yeah, and this v is like v itself, this column vector itself, okay. This is also a combination of column vector, like this one only, combination of column vector vector. So if you multiply with this, you will get this, okay. So don't worry if you don't understand the proof, that's not that much important. The conclusion that we get from the proof is important, but still, like I have proven it to you, like how I am getting the equation, right, how I'm getting the equation. So yeah, this is the v, okay. Now let me solve this. So this also I can write this as, this is a combination of column matrix, okay. So this is basically what this is. Now let me like expand this, okay. Let me expand this, let me write this. I will write this matrix as D matrix, right? I will write this matrix as D matrix, okay, or yeah, D matrix is fine, okay, or lambda matrix you can also write, okay, but I will write this as D matrix. Now let me write this in short format for me to easier to write, okay. This is A times V vector basically equals to V vector times D vector, D matrix, right? What I can do, okay, this is also like n cross n matrix only, and they are linearly independent. Each of the columns are linearly independent. So what I can do, I can take the inverse of this. Multiply the inverse on the like on the front. Or what I can do is to, like, if I want to find A, what I will do is multiply the inverse at this end, okay, at the post multiplication at the end. But if I want to find D, right, what I will do is multiply the inverse at this pre-multiplication, right, pre-multiplication. So first post multiplying. So post multiplying with V inverse. And why is V inverse existing? Because the columns, right, are linearly independent. The eigenvectors are linearly independent, and eigenvectors, each eigenvector is a column matrix itself. So post multiplying, right, what do I get? This is V only, and this is D only, and this is what? This is V inverse, right? So this breaks up as I only. Okay, so A times I is A only. So what is the final equation that I get? So final equation at A equals to V D lambda inverse. Okay, so this is the final equation. This is my final equation. Okay, so from here, right, I can find the value matrix of A if I know the diagonal matrix and the eigenvectors, right? If I know the eigenvectors, but the opposite thing is important. But with this property, what will be helpful? To find the powers of A, right? Powers of matrix A. So why is this helpful? Why is this property helpful? Why is the property helpful, right? Basically, right, if I want to find A square, right, what I will do, I will break this down in this format. I have A times A, right? Now what is A equals to? A is equals to this one, right? This one. V, okay, I zoomed in. A is equals to V D V inverse. Now again I will multiply with the same value, right? So this is V again D and V inverse. Okay, so what do I get? I get here is this is V inverse time V, which is I itself. So this becomes like this, breaks down to I itself, right? V D. Now I have I here. Okay, now this is again D times V inverse. So this is I times anything is that matrix only. So this is D times D. So what is the final result I get? I get here is V D square and V inverse. So what is the thing to notice here is, if I do the square, right, I don't need to do anything, just find the diagonal matrix square and the eigenvectors. I don't have to compute A square, I will directly compute this one. So let me write the relation, right? Let me write the relation. So the relation is basically like this. If I want to do any power of k, what I have to do is simply find the eigenvector of A itself, then just make the power of the diagonal matrix to the power k, raise it to the power k, and the V inverse, right? Take the V inverse. So you might say, like, I have to take the power of A, I have to take the power of D also. What is the difference? Why is it so much easier to compute this than this? The difference is, if we have only diagonal matrix, right, and other remaining elements are 0, what will happen, the diagonal elements will just raise it to the power of k, and that will be my diagonal matrix, like D to the power k. So let me say, right, let me take an example. Okay, this is the main property, so you have to like remember this. Okay, if I have some diagonal matrix, so let's say I have a diagonal matrix equals to A, right? So this is, let's say, equals to 2, 4 and 6. Okay, 3 cross 3 matrix, and other elements are 0. 3 cross 3 matrix. Okay, so what will be my A square? Basically, what will be my A square? You compute, okay, by yourself, but what you will find out is, just we are simply squaring the diagonal elements. So this is 4, 6, 36, 0, 0, 0, 0, 0, 0. Okay, that's why this is so easy. Now if I do the cube, right, if I do the cube, I will get what I will get. I will get cube, right? So again, so let me name this like D only, right? Not name this A, because that will be a bit confusing. So if I want to make D to the power k, what I will do is simply I will have the eigenvalues, right? I will just raise them to the power of what? K. Okay, so lambda 1 k, lambda 2 k, and this will keep on going on until lambda n to the power k. Okay, so yeah, this is 0 0, and this is going to keep on going on 0 0 0 0. Okay, 0 0, this is keeping on going on. Okay, so this is basically my matrix, right? This is basically my diagonal matrix, which is raised to the power k. Let me write the k better k and k. Okay, yeah, this is my diagonal matrix. So again, what will happen to the eigenvalues? So if diagonal matrix is going like this of e to the power k, the eigenvalues are this diagonal elements, right? So eigenvalues of e to the power k of e to the power k is simply what is it equals to? It is simply equals to lambda 1 to the power k, lambda 2 to the power k, and lambda 3 to the power k, and keeping on going on. And what is, like, let me take one example, right? So it will be very easier for us to find the eigenvalues. So this is also another property. Another property is simply what, like, this is an example. This is an example. Let's take an example. Simply eigenvalues of let's say A inverse. Okay, A inverse. What will be the eigenvalues of A inverse? So A inverse, right? Eigenvalues will be, like, tell me what will be. Lambda will be raised to the power, lambda will be raised to the power of -1. So lambda minus 1, lambda 1 minus 1. Oh, this is 3 cross 3. Let me tell this 3 cross 3. Okay, so lambda 1 minus 1, lambda 2 minus 1, and lambda 3 raised to the power of -1. So what does this mean? This means 1 by lambda 1, 1 by lambda 2, and 1 by lambda 3. Okay, so yeah, but what is the important point to note here? If any of these lambdas, right, are 0, then this will become infinity. What does this mean? Basically, inverse doesn't exist because the determinant is 0. Okay, so for this to be valid, right, the inverse should exist. That is, the eigenvalues should not be equal to 0. This to follow, inverse should exist. So lambda 1, lambda 2, lambda 3 not equals to 0. So this is one very important point. So right, so like, for us to use this property, okay, use this specific property, right, this property, or like you want to say like this property, this is the main property. This property, we have to find the diagonal matrix, right, D. That is the more important thing, diagonal matrix, and obviously the eigenvectors also. So how do we find the diagonal matrix? So what we can do is simply diagonalize A, right? That is the procedure for finding the diagonal matrix. Like that you can also find, like that is also another procedure for finding the diagonal matrix. But if you just find the lambda values, it's easy only, right? If you just find the eigenvalues, then also you can find the diagonal matrix. But if you want to find it some other way, there is also another way to directly find the diagonal matrix without without what do you say, the eigenvalues, right? So diagonalization okay, diagonalization. So let's say I have one example, a is equals to simply that previous example only, 2013. Okay, now what is it asking is to diagonalize a, right? Diagonalize a. Okay, so how will I diagonalize? So one thing I know, that a is equals to v d and v inverse. And what is v inverse equals to, so v inverse, right? What I can do is I have to find d this time. Okay, d this time. So what I will do is I will simply post multiply v and pre multiply v inverse. So pre multiplying v inverse with a and post multiplying v at this point, I will get I only. At this point I will get I only. So this is simply d. Okay, so I get my diagonal matrix, okay, which is v vector inverse a and v vector. Okay, so this is a very important form which will be used in the next few lectures, right? Which will be used in the next few lectures. So you have to remember this form. Obviously you can prove it, just take seconds. Okay, just take seconds. Just take seconds. Okay, so this was basically the d matrix, right? So as the question has asked to diagonalize, okay, so I will find the eigenvectors v matrix, then I will diagonalize this particular matrix, right? Diagonalize this particular matrix. Okay, let me put this question here only. Okay, this is also another question. Okay, let me put this above here. Okay, this is the proof basically. So how to diagonalize? First we change the color of this one. First find the v vector, right? Find the v vector basically. So for finding the v vector, again I will use the same procedure, that is 2 0 1 3 and v1 vector only. Okay, v vector for I will first find the for lambda 1 and for lambda 2, x1 y1. So what was the eigenvalues? Now I think it got stuck in your head, right? They were 2 and 3. I will take the first eigenvalue as 2. Okay, x1 y1. So again I will solve the equation. So I get 2x1 plus 0 equals to 2x1. So here, right, x1 basically can take any values, right? Any values. So x1 any values. Okay, and this one, right, x1 the second equation, that is, okay, let me solve in the next page. x1 plus 3 y1, x1 plus 3 y1 equals to 2y1 equals to 2y1. Okay, now x1 simply equals to minus of y1. Okay, y1 can also take any values, but the relation, what is the relation? That x1 should be opposite in sign of y1. So I will just take v1 as this one only. Okay, I will not elaborate it further, we have already solved this multiple times. Now what is for the v2? It is for, okay, let me write this bit proper. Now for v2, right, for v2 what do we have to do? For v2, right, again second eigenvalue, which is 3, right, which is 3. x2 y2 equals to 3 x2 y2. Again, what will be my x1 equals to, it will be 0, right? So 2x1 equals to 3x2. So sorry, not this is also x2. X equals to 0 only. Okay, x equals to 0 only. So, and what is y2 equals to, like, let me solve the second equation. So the second equation, right, again x2 plus 3y2 equals to 3y2 itself. Okay, so y2, right, x2 is 0 only. Now y2 can take any value. 3y2 equals to y2, 3y2 only. So y2 can take any value. So y2 any value. So again, right, let me take the first example only. This is 0 1. Okay, this is what my v2 vector is equals to. This one was my v1 vector. Okay, so not explaining it very further, we have already solved this, right? So now the diagonalization of a. Okay, diagonalization this is a tongue twister actually. Diagonalization of a, like, speaking this at night is very difficult actually. Anyway, sleepy and tired, but that's fine. Diagonalization of a. Okay, so what will be the diagonalization of a? It will be simply this v vector times this a vector and its inverse. Am I doing it opposite? Yes, I think I'm doing it opposite. Yeah, the inverse is at first. So you have to remember this, right? When is the inverse first and when is the inverse last? So there are two formulas, right? Just try to remember it conceptually. So inverse is first, right, for finding the D matrix, and inverse is last for finding the A matrix, or e to the power k, whatever you want to say. Okay, mainly we will use for finding the e to the power k, right? A raised to the power k. So yeah, so D matrix, right, will be the inverse of this. Okay, let me first write the normal V matrix itself, then I will write the inverse. So E, right, E is 2 0 1 3, and what is V equals to, this is the first, right, this is the first one, 1 minus 1, and this is the second one, 0 1. So 1 minus 1 0 1. Okay, now I will take the inverse of this. So what will the inverse for 2 cos 3 2 cos 2? It is very easy. Simply swap the ones, okay, and change the signs of the off diagonal elements and swap the main diagonal elements. So here the main diagonal elements are 1 only, so it becomes 1 1, and this is 1 and 0. Determinant is 1 only. We divide the by determinant, but it is 1 only. Okay, that's why we don't make any changes. Now we'll solve this. Okay, so if I solve this, right, so first I'll do this. So row times column, so 1 times 2 plus 0, so this is 2 only. And what is this equals to? 1 times 0 times 0 times 3, so this is 0 only. Okay, now this is 1 times 2 times 1 times 1, that is equals to 3 only. And this is 1 times 0 plus 1 times 3, so it is 3 only, right? So 2 0 3 3 I get. Now this is still the same, 1 0 minus 1 1. Okay, now what do I get? This is 2 times 1 and 0, right? So this is 2 only, and this is 2 times 0 times 1, this is 0 only. Okay, now this is 3 times 1 and 3 times minus 1, so this is 0 only, right? And this is 3 times 0 times 3 times 1, so this is 3 only. So yeah, we got our diagonal matrix. That was basically this eigenvalue lambda 1 and lambda 2, and this is my diagonal matrix. So this is how we do the diagonalization basically. So obviously if we have been given the eigenvectors and the matrices, then we can do it, but obviously that's not the case most cases. So yeah, this is just to show you like how we do the diagonalization, right? So this is lambda 1, this is lambda 2. So yeah, this is the procedure of diagonalization. But one thing to note is that we can't diagonalize every matrix. Why? Because for us to diagonalize, the eigenvectors must be independent of each other, right? So we let me write this. Diagonalize the matrix only when eigenvectors are independent of each other. Okay, independent of each other. So from here what can we deduce, right? If I say to you, if the eigenvalues are distinct, right, then can we diagonalize that matrix? For a matrix, if the eigenvalues are distinct, can we diagonalize that matrix? The answer would be yes, we can. Now if I say, if the eigenvalues are repeated for a matrix A, can I diagonalize that matrix? So what will be your answer? So if your answer was no, then you are partially correct, okay, or you can say partially incorrect, because even if the eigenvalues are repeated, as I mentioned previously also, the eigenvectors may be independent, right, or they may be dependent. Okay, they may be dependent or they may be independent. Okay, so because different eigenvectors can scale by same factor. They are in different direction, but the scaling factor may be same, right? That doesn't matter. Okay, so that is one point to note. Now if one of the eigenvalues is 0, then anyways we can't do diagonalization, because eigenvector will be for sure we can say eigenvector will surely depend on the eigenvector will be surely be dependent on the other columns, right, on the other eigenvectors. So yeah, then definitely we won't be able to diagonalize this matrix. So what can we deduce? Eigenvalues distinct can diagonalize. Okay, let me copy this. Eigenvalues if they are repeated, right, repeated, will depend on eigenvectors. Okay, and if eigenvalue is 0, then definitely we won't be able to diagonalize, can't diagonalize, because the eigenvectors will be dependent on each other, right? Because that matrix will be 0, the determinant will be 0. How is it 0? Because one of the column will be dependent on the other columns. So can't diagonalize. Okay, yeah. So this was the basic important point. Okay, also another point to note here is like this property, right? That this property that I told you, this will only be valid when the V inverse exists. This will only be valid when V inverse exists. This is only valid for simply when like we have like distinct eigenvectors. Okay, so by that only like this V inverse will exist, right? By that only this V inverse will exist. So only valid for distinct independent eigenvectors independent. Okay, let me write this in a better manner. independent eigenvectors, right? So yeah, also when else is this valid? Okay, why did I go? When else is this valid? So this is valid, right? This is definitely valid when always valid for distinct eigenvalues, because if my eigenvalues are distinct, then definitely my eigenvectors will be independent. Always valid for distinct eigenvalues. Okay, so let me make this a bit bigger, and let me make this a bit smaller. Here, let me take this here. Yeah. So yeah, these were the few points that I wanted to tell to you, like explain to you. Okay, say to you, whatever. My English is not that great. So yeah, let me do another question. Okay, let me do another question. So this is also another important question basically. So this is mainly for maths, right? Maths purpose. So I'm solving this for maths also. So this lecture will be like for the maths people also. So this, right, let's say I have one equation of a to the power 4 3a square, okay, plus 3i. Okay, now what I want you to tell me is what will be the basically determinant of this whole equation. What will be the determinant of this whole equation? So how shall I find it? So how we will find it is simply, you don't have to solve, right? You don't have to solve. What you will do is let me take this as example only. Simply you will write this in the diagonal format. So again, a raised to power 4, what will be a raised to power 4? A raised to power 4 will be simply d raised to power 4 only. Okay, and what will be a square? It will be 3d square plus 3i. Okay, and we have to find the determinant. From here it is easy for us to find. Okay, d to the power 4 is easy for us to find, d to the power 2 is easy for us to find. Okay, so this is equals to 0. Okay, and this will be easier for us to find, but this is only possible only when V inverse exists, right? When V inverse exists, okay. So yeah, this, what did I do? I wrote a in terms of this one, right? This property I used, where was I? Not this one, this one, right? This property I use. So again, what happened is that simply what will happen, that v and v inverse will get cancelled. How? Let me explain it to you. So if I like expand this, right? If I expand this, what will happen? So this a raised to power 4, what will happen? This will become v. Okay, I hope you remember if v comes first or v inverse comes first in case of a, right? So this is again d to the power 4 itself, and this is v inverse, right? Okay, now what do I have? I have 3, this is v itself, this is d square, and this is v inverse itself, plus what I can write I as 3 times v into v inverse. Now I will do some trick very smartly. What I will do is, okay, let me cut this and paste this over here. Okay, let me change the color. This color is not suiting this one. So what I will do, this is the determinant, right? This is the determinant. Okay, this is the determinant. So if this is the determinant, basically what I will do, I will take common this v and this v inverse at both ends, right? At both ends. Okay, so if I take common, right, so I have this determinant, I'm taking common of v matrix at the starting. Okay, and again this equation is same only, so I'll copy and paste this one only. let me write this here. Okay, let me delete this, this and this, right? So this is coming here only, minus 3 t square d, and this is like this one. Okay, let me break this down here. This is the inverse, right? Now what is the important thing to note here is I can simply take this out, right? So determinant of a matrix, it is in multiplication, so a determinant of a into b I can find individually, determinant of a times determinant of b. So this is the basic property. So this will be equals to determinant of v, and this is the between equation, right? Between equation, determinant of this one, and this is basically the determinant of v inverse. So right, this is just a scalar factor, right? So I am multiplying by determinant of v and I am multiplying by 1 by b, determinant of 1 by b. So these can cancel, right? These can cancel each other out. So this will what remain at the final equation. Okay, this is what I will get in the final equation. So yeah, simply that is equals to 0 only. So that's why like I get it directly here. So like I was first writing there because I wanted to like see if you are able to grab that or not. Okay, so yeah, obviously I have to expand. So yeah, this was basically it for eigenvalues and eigenvectors. Thank you for watching, and in the next lecture, right, in the next lecture we'll mainly now study the different forms to how to represent state space equations, right? That's why we studied all this. Okay, yeah, thank you for watching.